So the next series of sensors we're going to talk about if we're interested in measuring the velocity of a of an object. So if we're interested in linear velocity, all right, basically all velocity measures have to be made with respect to some type of reference plane. So for example, your car speedometer tells you actually measuring the rotary velocity of the transmission or drive shaft with respect to the frame of the car. And then that rotary velocity is then converted to a linear velocity. All right. For direct linear velocity measurements, what's often done is that displacement signals, like the ones we talked about for an LVDT or a linear encoder, are used, or an acceleration signals from an accelerometers are used. So the pros and cons listed are listed below for using both position and acceleration. So position on the right, acceleration on the left, all right, to determine velocity. All right. So, um, so typically positions are good for if you're interested in measuring the velocity over larger time frames, while accelerations have large errors associated with those. But over short time frames, they're very good, and they're not affected by noise. The issue with using position measurements is if they have a lot of noise in the measurement, that noise can affect the position measurement by quite a bit. You can eliminate that effect a little bit by using a moving average filter. Um, uh, so just to show you examples of what that looks like, is if we have a signal here, all right, and this is our original data, all right, this is our uh, original data from our transducer, all right, y of t, all right, and we have another, we integrate that signal. All right, in the case of the accelerometer, what we would get would be something like this. All right, a very nice, smooth, consistent signal. All right, now if we if we differentiate that signal with respect to time, especially the noisy signal, we end up with a measurement that looks something like this. So this the derivative doesn't really represent the reality of what's going on, while the acceleration signal did a much better job when we integrated that signal of actually representing the reality of the motion. Okay, so what you can do to avoid this from happening is if you did a moving average, all right, you would get a result that would look a lot better or a lot closer to this. Okay, so now there are a few sensors that can measure velocity directly. So the one is called the moving coil transducer, which basically works by having a series of coils. All right, so these are circular coils that go all the way around a permanent magnetic field, and as these coils move up and down, that creates a change in the um, the voltage output, which is proportional to the applied velocity and some constants. All right, so the constants are the magnetic field, the coil length, the coil diameter, and the number of coils. All right, so basically this term here is your calibration constant. All right, and using that calibration constant and the output voltage, you can estimate the velocity. Okay, so in the next video, we're going to talk about how we measure angular velocity measurements. Um, so, which is probably most important for understanding motion of motors and other rotary devices.